ends up being too hot. So, all right, so we're starting off with A1. A1 is US pigment with some borate, so this one will have a little lower viscosity. This is a cobalt iron mix. Bold move. Bold. So this will be sort of like a greenish tinted blue, probably, with sodium sulfate. So hopefully we've knocked down the bubble content. So A1, front and center. All right, go ahead. That's good. All right, a little bit closer to the bead. Yep, that's good right there. The inner cones should be touching the glass. All right, now fire polish with the inner blue. A little bit closer, right there. Nope, keep going. Okay, that's probably pretty good. And so now we can stamp. So normally you just kind of move from the side, right about there. Nope. Well, okay. The bottom edge typically is where you're gonna do it. It's all right. So that way it
always the first.
Yeah. It sometimes a middle stamp can create a little bit of stress in the middle. But it'll probably be fine.
That's right. That's where I naturally wanted to put it. So.
Yeah, right in the middle. It is a logical place to put it. But as you watch these glass compositions, you'll often see a color change over time. In glass terminology, it's called when the color strikes, the striking point of the color. As it cools, the metals are actually coordinating with oxygens in the glass at different ratios until finally it gets to its final ratio. And so for some of them, they don't hit their final color until they're significantly cooled down. So we'll see what happens in this case. But we're still kind of a bluish, or kind of a greenish blue, but it seems to be darkening for my eye a bit as we go. All right, so that was...
What was it? Pretty one. Was that pretty low viscosity?
That one was fairly low because it poured out pretty easily. That's likely accentuated and caused by the borate. The borate additive knocks down the viscosity because it melts easier than the silica. So that's a pretty common thing. All right, so next up we've got B1. And so this is with silica sand, not the pure silica, but the white sand, which is fairly pure sand. We're using washing soda, calcium carbonate, and chrome this time. Chrome oxide, 0.2 grams. So that'll look different.
You can hear the glass cooling down.
Yes, so eventually there'll be a chorus of noise coming from over here. And you hear these little like these high-pitched sounds. What that's called is crazing. Crazing, and it's caused by the fact that the ceramic has a different coefficient of expansion as the glass, and as the glass solidifies and the differential shrink continues to happen, it's popping all these little microscopic cracks that eventually become macroscopic cracks. You can see them forming right there in front of our very eyes. And so once we get like, 5 to 10 crucibles over here, it'll be a constant chorus of this noise. And if you're watching, you would see cracks forming constantly. Every sound is a crack forming. Yeah, we're deepening in some more blue now, not green. So, okay. So let's do B1, and we're pulling from the left. Okay. Try again. You got to flame it first. There you go. Lower viscosity on this one. And just a little bit closer with the torch. It's good right there. So the tips of the blue are the hottest point.
Sorry. Switch hands.
And we can get you a glove if you need to.
Next time, yeah.
so then right about there you can stamp, and usually stamp from the other side so you're not over the hot glass from before, and just into the lower edge there. And you gotta hurry. There you go. Yeah, so it's a constant kind of game of timing there, because the glass is cooling and changing in viscosity as you go. So, but the good news is it's no big deal. We're just making glass samples for observation here. But yeah, the radiant heat is quite a thing to behold. Now, interestingly, with the chrome, it starts off brown, and then it cools a little bit, and then it suddenly becomes green. Did you get toasted a little bit there?
Yeah.
Put some jam on it?
No, we're good.
Yeah, so the glove should help. All right, so next up we'll put one here.
I think we should be writing down notes on the lab sheet, right? For this?
Yeah, so you can record like the viscosity. Now it should be recorded, so you can review it. Yeah, it'll work out.
You said that one was lower viscosity?
So this one, I'm sorry, had a greater viscosity.
It was medium.
Could be medium, yeah. And you'll notice the disc is smaller, and it did pour out a bit slower. So those would be the observations.
So what are we comparing the viscosity to? Is it all compared to, is it on the data sheet it says compared with A, so are we comparing it based off of the first batch?
So A is,
I guess I'm wondering how we rate it.
this is the standard A that we used in the past. So this batch is pretty typical base viscosity.
Don't put that
So
in the video. Show.
yeah, sure, we can do that. And you can sort of rate the standard size with A, and that'll give you a good idea of how they compare. After this cools, there's rulers over there, and you can use that to get a cross diameter and then rank based on diameter. And that gives you a semi-quantitative indication of viscosity. We're not relating it to the actual units of viscosity, but we're using the size of the disc greater size equals lower viscosity. So it's an inverse proportional relationship with the size of the glass disc, because we're using approximately the same amount each time. So that's one way to benchmark that. So. All right, so let's do composition C now. This one yours?
Yeah, I.
Okay, so composition C is a mix of silica and sand. It's quite a mix of various different sands, and so this is probably a nice mix of all the sands we had, plus a little bit of the pure silica. We've got a mix of sodium carbonate and washing soda, so a mix of sodium flux, calcium carbonate, limestone, dolomite. So this will have some inherent iron coloring because of the iron impurities in the sand. And then to that we added 0.2 grams of manganese. So purple plus green. I think that tilts it towards brown, I think. So we'll see. Purple plus green, where we're going to end up. All right, so this is composition C pulling from the right. You've got some bubbles there. So hit those bubbles too with some of your time. Try to get those to pop and pull in. There you go. Alright, that's good. That's a super low viscosity. See how there's a really high recovery from the crucible? So that's good.
Okay.
Now, I'm thinking that because we had such a variety in the different silica, the impure nature actually can help it melt more easily. So that one definitely, yeah, so we're moving towards some brown. We'll see where we end up. Can be kind of a greenish. The manganese color will kind of tilt that maybe to darker brown as it cools. These are now more convincingly blue and a nice green there. So good, some nice variety of color there. Thank you. So next up is D1.
It's almost golden, sort of before brown.
Yeah.
It's kind of gold.
It is kind of a yellowish, very bright gold color there. All right, so for D1, we've got white sand, we've got limestone, we got sodium carbonate, and this one just has a medium-high load of manganese. Remember, that's the purple color, right? And so we should hopefully get a light purple out of this.
What would you say the flux is on that one?
So on this one, the flux is the sodium carbonate and the limestone. The crushed limestone also acts as a strengthening agent. So the limestone's a dual purpose, flux plus strength, where the sodium carbonate is just flux. All right, so this is composition D1.
Middle.
And pull it from the middle again, yeah. A little bit slower right in the middle there. When I
Yeah.
ceramics going crazy. So tilt the flame more towards me. There you go. Alright, just like clockwork now. Got all our training.
Oh, big glass.
Yeah, so this is fiberglass. Now, I gotta warn you, this looks like it'd be fun to play with. It gets you. So the problem with fiberglass is it's flexible, but this is thick fiberglass. And so what happens is you're playing with it and you're like, yeah, this kind of bends, but then all of a sudden it breaks and then straightens and it just pokes right in you like an automatic nail gun, which I actually have. You know what's about to happen, right? I'm putting nails in and it curves like this. Sometimes they take a curved path when they're thin, and I have nailed into my thumb before, and it's like, ah! So I survived, but it was exciting. And so it happens, and you get these little pieces of glass right into your fingers. And so I'll be trying to manage the fiberglass so that they're less of a hazard right afterward. I will file the edge of the crucible to get that off, so you can look at the crucibles later. But resist the urge to touch fiberglass. It's bad news for you. So, all right. So
Should I go from
no, you can go across the most recent row, but try to avoid the previous.
Gotcha.
All right. So that was D. Next up is E. So this is mason sand, silica sand, and borate. So that's going to be a low viscosity, I think. The mason sand tilts it a little bit inherently greenish yellow with some extra purified silica. So mixed silica batch, washing soda, sodium carbonate, calcium carbonate, dolomite. Nice mix on this one. It says magnesium oxide, but I think it's manganese oxide. Manganese oxide.
That's purple.
Yeah, purple, and this is 0.22, so a higher load. So what we're expecting on this one is it will have a little bit of yellowish color with a darker purple. So I don't know, we'll see where that ends up. But we'll pour that one right there. So E1.
Watch that.
Tilt it a little more toward me. There you go. the heat that you see, or the color that you see to begin with, is called black body radiation. It's called black body because in a darkened room or in outer space, the crucibles by themselves have no inherent ability to give off light. And so that's it's not luminescent matter. So they call it black body radiation. So once it starts heating up, the simple agitation of the electrons themselves thermally give rise to this continuum that all matter exhibits when it is at high temperature. And so as that's bleeding off that heat, we see a change in the light that it's giving off. If you do enough of this type of work, you can train your eye and determine to probably plus or minus 50 degrees the temperature of what you're looking at. So this bright orange is very typical for 1100 or the 1150. White hot is more the steel casting regime, and so that's on up into 14, 15, maybe even 15 to 1600 Celsius. So another interesting thing to be watching and thinking about. So right now we're still kind of yellow-ish. So
What
all
was
right.
the viscosity of that one?
It was lower. It's a bigger disc.
About
It-
like eight.
I mean, some people just try to say low, medium, high. Some people have it ranked 1 to 10. You'll be able to verify that with a ruler later on. But if you're trying to go semi-quantitative or just qualitative by just saying low, medium, high, or semi-quantitative is kind of nice because you can probably rank them 1 through 10. But there's not like I'm mostly wanting to see your effort to compare them. I don't have necessarily an exact number in mind. So next up, we'll put next composition there, which is F1. Silica Sand, MC. That's my MC here. Silica Sand, washing soda, crushed limestone, some more manganese dioxide, and some sodium sulfate, which should help clarify some of the bubbles, perhaps. So another manganese, this time with any impurity that's present, so any tilt away from purple will be caused by the limestone in this case, the crushed limestone. Maybe a touch in the granucell sand. So manganese dioxide seems to be a popular colorant. So
It's on the right.
on the right, okay. Not pretty sluggish there. Now really hit that top part here with the pull in. Okay, looks good. Alright. So is the glove helping with heat management? Oh, yeah. More fiberglass here to deal with. Piece flying across the room.
That was a little bit like medium viscosity.
Yeah, it was kind of it was low for sure. Yeah, so feel free to kick that underneath or just kind of put the fiberglass in the crucibles. There is usually where I store them till the end. Once you're done taking a peek at it, you can just put it into the crucible. That's definitely dark purple, way darker. So that's nice to get a nice dark purple there. Some good coloration. We had one year, I may have already mentioned this, where we somehow ended up with browns and greens, and that was it. And they were all dark, and it looked like what I called the Realtree collection. They all look like camo glass. It's like the cathedral in the woods you're trying to hide. You know, make camo Realtree stained glass windows. Deer hunters and stuff would be awesome. Probably not, 10th century Europe material, but hey, if you're gonna have a cathedral in Wisconsin, why not make it camo, right? So, silica sand. So that's the granusil, Grusely borate. So we're gonna have a lower viscosity likely from the borate. Washing soda, crushed limestone, cobalt oxide, sodium sulfate. So blue on a fairly pure batch with the white sand and the crushed limestone. But this has more just earthy ingredients, a lot less processing in this case. These are mostly fairly pure minerals, but they're not processed chemical grade. So, all right, so we'll put that one here, and our letter is G1. Gloves on fire. Yeah, there are some bubbles. Those might be small enough that we're probably still stable. The big ones are the ones that are pretty bad news for stability. One thing I've noticed is that the borate separates so much easier. I don't know if you've noticed that, but if there's borate present, when I pull away, it just kind of strings right apart. Where the non-borate additive glass, it seems like it pulls on and strings a lot more. So, nice variety of color this year. That's good for this semester.
Like a greenish.
This is going to end up in the cobalt palette, and it's going to be similar to this one, but maybe not quite as dark, because this one I think has some additional iron impurities. This one just gets a touch of iron impurity from the crushed limestone.
Just a shade.
It's just a little. It's in the same palette as the first one we poured, but and it should be. You know, it's a similar color load. So, all right. Next up, we have H1. It's a 50-50 mix of mason sand and silica sand. So it's medium impurity. Mason sand's about as iron impure sand as you can get. So we're cutting it with the white sand. So it'll be half that load. We got sodium carbonate mixed with washing soda for our sodium source flux. Calcium carbonate crushed limestone. So we're half and half, kind of the pure and impure. And then this one's interesting. It's a mix chrome copper. So green plus blue, and I think this is our first copper example. If you look at copper on the periodic table, number 29 there, it's in the column that's called the noble. It's one of the least noble of the noble-like metals. What that means is that it has a high tendency to be reduced. The carbon monoxide, believe it or not, in the middle of that flame is enough to reduce the copper. And so for this one, what I'd like you to do is a little more fancy torch work. So you're going to be torching it as you normally did, but then as you're torching toward the end, get very close to this edge and just fire polish 1/2 very, very close.
Okay.
And what will happen is you'll see the regular glass color on one side, and hopefully the carbon monoxide in the flame will reduce a surface layer of copper, and it will flash to metallic copper mirror on the side that you give the closer treatment.
Sounds good.
And so in order to do that, it has to be kind of toward the end, but not after it's completely becoming clear. And so we'll just kind of eyeball it, but get very close with the tip, and that should reduce some of that copper, which would be kind of cool. So green plus blue plus copper mirror is what we're after. So put that one right there.
To the left.
Yes, H1 to the left. So hit the top first and then do that polishing for a while on the edge, even a little closer. That's probably good. Let's see if we got there. It works very well for the regular copper. It becomes a little more uncertain when you have other metals present. But my guess is we'll see some effect. Some bands of shinier copper. Yeah, I see some popping in there.
Yeah.
A little more subtle, but there's some banding that's here on the side that you'll be able to see eventually that's really copper colored. All right, so next up, we'll put that one here, and then we'll probably chart some new territory on the back plate there. So next up we've got I1. So we've got pure silica, silica sand, and mason sand. So this is a 30-30-30 mix to get up to 90. So interesting. Mixed sodium carbonate and washing soda, limestone, 0.2 copper oxide, 0.1 manganese. So this is going to be purple blue. First example of that. So this one can also exhibit the copper coloration, and so I'd say do the same treatment and get the tip even closer to the edge on this one. It should be like half a centimeter.
Okay.
You want the inner cones to be hitting the surface because that bright blue is where the carbon monoxide is still hanging around.
Gotcha.
And so we'll end up with hopefully a blue tilted purple with copper mirror. All right, I1
It's on the right.
on the right. And I'm just going to flash over the surface more quickly, all over real close. There you go. Looks good. Okay. It might also be, we've got a little lower copper loading than when we, it's all right. It just needs to finish cooling down a bit, but yeah, it's kind of wrapped. Okay, so now we've got 3 more.
Yep.
Okay, so we may just keep trucking right on across the back here. Adjust the camera a little bit to capture that. Getting a new liquid nitrogen delivery, it sounds like.
Tell by the screen.
Well,
I know it won't be.
either that or they're dropping large metal objects on the floor over there, which would be bad. So, all right, here we've got a full copper. So this one will definitely show that copper mirror.
Same thing again.
What's that?
Same thing again.
Yep, same thing.
Okay.
And so this is U.S. pigment, pure silica, sodium carbonate, calcium carbonate. So we're going for pure ingredients plus coppers. This will be a nice, straight, bright blue copper color. So that'd be nice to compare with these other ones. So we'll put that one right there. J1
In the middle.
in the middle. Okay. break off.
Oh, it swirls in that.
What's that?
The
There's a lot
swirls.
of swirls in it.
Yeah, so that's the copper, reduced copper particle in the surface. Yeah, so it'll be kind of just a swirl of metallic copper on top. Kind of adds some character. All right, so two more, right? So K1, pure silica, pure carbonate for both sodium and calcium, and copper again. This is like take two. So this one should be very similar. Almost across the board. The only difference, it looks like, is there's a slightly lower copper loading at 0.34 and a different type, slightly different type of calcium carbonate. When we just did use the heavy, this one uses the light powder. Currently I have a call coming in. I'll deal with that later. So, all right, we ready to go?
Back left.
Back left. Okay.
Something making.
Bee stinger waiting to get somebody there.
And we're going to W?
Yeah, W, we did have the group that added a later batch. So the lettering is discontinuous, but
Just W.
it's still unique. It's still between the two sections. It's its own.
You ruined the groups of 3x3.
Well, we'll still get one more group of three, right?
No,
So,
in the past.
oh right, yeah. Okay, so this definitely looks like the bright blue copper. So we'll see if that one ends up matching it. That one ended up being a little more viscous, kind of interesting. Not sure why. All right, last one. W. Purified silica mostly, a little bit of white sand, sodium carbonate, calcium carbonate, plus chrome. So this one will be our straight chrome batch. 0.2 loading, which is pretty typical. So this will be like the, kind of like this one, but I think this one uses a different silica matrix. But this will be sort of like the 7-Up bottle green is what this one should usually look like. So we'll put that one right there, finish out the set.
It's the last one in there.
All right, sounds good.
Just a little bit more.
Yes.
Come on.
All right. Good job. Thank you for your help. We now have to wait half hour or so, I've got a couple different videos demonstrating behavior of glass and